Welcome back, everybody, for another deep dive. Today, we're going to be talking about cloud computing, and specifically kind of a battle that's brewing between WebAssembly and Linux containers.
Okay.
You did some research on this,
Yes.
specifically a master's thesis.
Yes, by Jasper Alexander Wiegrutz.
Okay.
And yeah, it's a comparison of WebAssembly and Linux containers in a Kubernetes environment.
So let's dive into this and see what's what. So first of all, I think it would be useful to sort of set the stage and talk about some of the fundamental concepts and landscape that these two technologies operate in.
Okay.
When we talk about cloud computing, what are we talking about?
Well, cloud computing is basically just the on-demand availability of computer system resources like data storage and computing power without direct active management by the user.
And so how does that relate to virtualization?
Well, the foundation of cloud computing lies in a concept called virtualization. And this concept dates back to the 1960s, and it allows us to create virtual instances of computer resources.
Oh,
So imagine a single powerful physical server. Through virtualization, we can divide this server into multiple virtual machines, each functioning as an independent computer with its own operating system and resources.
gotcha. And so this is sort of the basis of infrastructure as a service.
Precisely, cloud providers will lease these virtual machines to users.
So that's virtualization, but then at some point containers came along. So how do those fit into this?
Well, containers offer a lighter and more agile alternative to virtual machines. Unlike virtual machines, which include a complete operating system, containers share the host operating system's kernel while providing isolated user spaces. This architecture results in significantly faster startup times and more efficient resource utilization factors that contributed to their explosive popularity with the emergence of Docker in 2013.
Okay. And so I guess in addition to containers and virtual machines, there's also this whole ecosystem built around them. So what is that all about?
Indeed, container engines like Docker and Podman manage individual containers on a single machine. At a higher level, container orchestration tools, most notably Kubernetes, manage containers across large distributed systems, ensuring reliability and scalability. Kubernetes acts like a conductor, orchestrating the complex interactions between containers.
So where does WebAssembly fit into all of this?
Okay, so WebAssembly is entering the cloud arena. It was initially designed for speed, safety, and portability within web browsers, but now it's being explored for server-side applications, and with some even suggesting it could potentially replace containers. Solomon Hykes, the founder of Docker himself, has stated that if WebAssembly and its system interface WSI existed in 2008, Docker might not have been necessary. It's a bold statement that highlights the disruptive potential of WebAssembly.
So it seems like there's some pretty high hopes for WebAssembly. So technically, how does this all work?
So to fully grasp this disruption, we need to delve into the technical details. The WebAssembly virtual machine provides a secure, sandboxed environment for code execution. WSI, or WebAssembly System Interface, enables interaction with system resources, but in a carefully controlled manner using a capability-based security model. This means that WebAssembly programs are granted access to specific system resources only if explicitly permitted, enhancing security and limiting the potential damage from malicious code.
Okay, so it's like running code in isolation, but with very tight control over what that code can actually access.
Precisely. Now, the thesis that we're examining today focuses on the security and performance differences between WebAssembly and Linux containers within a specific environment, a modified OpenShift platform, which is an enterprise-grade Kubernetes distribution.
All right, so in this thesis, what are some of the specific security and performance aspects that were looked at?
The security analysis focuses on simulating real-world attacks, particularly code injection and privilege escalation, to assess the practical implications of these vulnerabilities. The performance benchmarks, on the other hand, evaluated metrics such as startup times and computational performance in a function as a service, or face context, a common cloud computing paradigm where code is executed in response to events or requests.
Okay, I see. So let's start by talking about code injection.
Sure.
So how does this work, and what are some ways that this can be exploited?
So code injection attacks involve malicious actors attempting to introduce harmful code into a system. Container images, being the building blocks of containerized applications, represent a potential entry point for such attacks.
Okay.
The thesis explores two primary scenarios for code injection. The first involves an attacker replacing a legitimate container image in a registry like Docker Hub with a malicious one. The 2019 Docker Hub data breach, where usernames and hashed passwords were compromised, serves as a stark reminder of the vulnerability of container registries.
So essentially, someone could swap out a good container image with a bad one, and then when someone goes to download that, they might get the malicious code instead.
Exactly. And the second scenario involves a man-in-the-middle attack where the attacker intercepts the container image as it's being downloaded from the registry, potentially injecting malicious code during the transfer.
Also, they don't even have to replace the image in the registry. They can just kind of intercept it on the way to the user.
Precisely. And this underscores the critical importance of secure OCI transport protocols, particularly the use of TLS encryption. Insecure configurations using plain HTTP or weak TLS setups expose container deployments to such attacks.
So it sounds like these attack scenarios would apply to both Linux containers and WebAssembly?
That is correct, as both rely on similar distribution mechanisms for their images.
Okay, so how can these risks be mitigated?
The thesis emphasizes the importance of signature-based authentication for container images. This involves using GPG keys to sign images and then verifying those signatures before executing them, ensuring the image hasn't been tampered with. The research demonstrates the effectiveness of this approach in preventing malicious code injection for both Linux containers and WebAssembly.
So it's kind of like a digital signature that verifies that the image is what it claims to be?
Yes. And while signature verification is a crucial step, it's equally important to consider the role of the operator managing the Kubernetes cluster. They are responsible for managing trusted GPG keys, a task that carries significant security implications.
Oh, right, because if the attacker can compromise the keys, then the signatures aren't going to be very useful.
Exactly. The thesis recommends exploring more robust tools like Cosign and Sigstore for enhanced security, especially in production environments.
So that's code injection. But what about container security? So how does that work?
Container escape refers to the scenario where malicious code already running inside a container attempts to break out of its sandboxed environment and gain access to the host system. The thesis outlines various attack vectors for achieving this, including exploiting misconfigured volume mounts, which allows sharing files between the host and the container.
So if a volume mount is misconfigured, it could give an attacker access to sensitive files on the host system.
Precisely. Attackers can also exploit vulnerabilities in the container runtime itself, or even in the underlying kernel of the host operating system.
So it sounds like there are quite a few potential weak points that an attacker could target.
Yes. Another significant risk arises from granting excessive privileges to containers. Running a container in privileged mode grants it full access to host resources, essentially handing over the keys to the kingdom to potentially untrusted code.
Right. If you give a container too much power, it's basically like running the code directly on the host.
Exactly. The thesis actually demonstrates a privilege escalation exploit where an attacker manipulates C groups, a Linux kernel feature for resource management, to gain root access on the host system.
So even something like resource management, which seems fairly benign, could be used to gain unauthorized access.
Unfortunately, that is correct. Now, when we shift our focus to WebAssembly, the security landscape becomes even more intriguing. With WebAssembly running inside a container, we have two layers of isolation. The WebAssembly sandbox itself, known for its memory safety and fault isolation properties, and the container environment.
So it's like having two security guards instead of one.
That's a very good analogy, but it's important to note that the thesis didn't just rely on theoretical assumptions. It put WebAssembly's security to the test.
And what did they find?
The research successfully demonstrated a privilege escalation attack from WebAssembly within a privileged container. However, this attack was significantly more complex than escaping a traditional Linux container. It involved manipulating raw disk access to change the root password, a less conventional and more challenging attack vector.
So escaping a WebAssembly container isn't impossible, but it seems significantly more difficult.
That's right.
Now, this analysis focuses on a specific WebAssembly implementation within Kubernetes, so it's worth mentioning that these findings might differ with other runtimes or outside of the Kubernetes ecosystem.
That is a very important point. Security is an ongoing concern, and continuous research and vigilance are essential.
Okay, so we've talked about security. Let's move on to performance.
All right.
The thesis dives into startup overhead, a critical factor in FES environments where rapid scaling is crucial. So how was startup overhead measured in this research?
The researchers used a minimal Hello World program written in Rust, compiled it for various targets, including native x86 and WebAssembly, and then measured the execution time across different scenarios. These scenarios included native execution, containerized execution with Podman, and execution with different WebAssembly runtimes like WASM Edge and WASM Time. This allowed them to compare the performance impact of different execution environments.
Okay, so it sounds like they were comparing apples to apples as much as possible.
Sorry.
So who wins the startup race?
Well, as one might expect, native binaries executed directly on the hardware without the overhead of containerization are the fastest. However, the research highlights that containerization, regardless of whether you're using Linux containers or WebAssembly, introduces significant overhead due to the time required to set up the container environment.
Okay, so containerization always adds some overhead, but
Yeah.
what about the WebAssembly runtimes themselves? Do they add any additional performance penalty compared to running native binaries within a container?
Yes, they do. The thesis provides detailed comparisons between WasmEdge and WasmTime, showing varying startup times. WasmEdge in particular was significantly slower, especially without pre-compilation, a technique that compiles WebAssembly code ahead of time for faster execution. However, interestingly, all WebAssembly runtimes exhibited faster startup times compared to statically linked native binaries.
Oh, that's an interesting finding. So even though WebAssembly runs within a virtual machine, it can outperform certain native binaries in startup time.
It appears that way, at least in this specific test scenario. It's worth noting that startup time is just one aspect of performance. We also need to consider overall computational power for more complex tasks.
All right, so let's talk about computational power. What kind of benchmark did the thesis use for this assessment?
They chose to implement the Merkle tree algorithm in Rust, a computationally intensive task relevant to various real-world applications, including blockchain technology.
Could you explain what muckle trees are and why they're important?
Of course, a Merkle tree is a data structure that allows for efficient and secure verification of data integrity. It's a tree-like structure where each node represents a hash of its children. Merkle trees are widely used in blockchain systems like Bitcoin to ensure that data blocks haven't been tampered with.
So it's not just some made-up algorithm for the sake of the benchmark. It has real-world applications.
Yes, very much so.
So what were the findings of this benchmark?
Once again, native binaries demonstrated superior performance in terms of speed. However, the performance gap between WebAssembly and Linux containers was much smaller than observed in the startup benchmark. This suggests that WebAssembly, while potentially slower off the starting line, can catch up when it comes to sustained computation.
Okay, so it sounds like WebAssembly might not win every race, but it can definitely hold its own.
Precisely. Now, the thesis also observed a rather intriguing phenomenon. Statically linked native binaries perform significantly worse than dynamically linked ones, and even worse than some WebAssembly runtimes.
Oh, that's interesting. It seems there are performance trade-offs even within the realm of native binaries.
Yes, static linking, while potentially saving space, can come at the cost of performance.
Now, in addition to general computational benchmarks, the thesis also examines a specific use case with significant security implications, cryptography.
Yes, that's right. They focused on the performance of the Argon 2 password hashing algorithm.
Argon 2 is known for being memory hard, right?
Yes. That means that successfully cracking an Argon 2 hash requires substantial memory resources, making brute force attacks significantly more difficult. The thesis specifically chose a deterministic hashing task avoiding random number generation to ensure consistent and repeatable benchmark results.
So how did WebAssembly perform in this cryptographic showdown?
Native binaries, specifically those running directly on by86 processors, excelled in this scenario, suggesting that Argon 2 might be optimized for by86 architecture. WebAssembly runtimes, on the other hand, were noticeably slower, indicating a potential performance gap for tasks heavily reliant on specific CPU optimizations.
So if you're dealing with computationally intensive cryptographic tasks, native binaries running on by86 architecture might still be your best bet, at least for the time being.
That seems to be the conclusion based on this research. However, this highlights a key strength of WebAssembly. Its portability. WebAssembly is designed to run on any platform with a compliant runtime, regardless of the underlying CPU architecture. This portability becomes a significant advantage in a world increasingly dominated by heterogeneous computing environments, where applications need to run seamlessly across a variety of devices and architectures.
So while WebAssembly might not yet outperform native binaries in all scenarios, its portability offers a compelling advantage in the long run.
Indeed. Now, stepping back to look at the bigger picture, we've examined both the security and performance aspects of WebAssembly and Linux containers, highlighting their strengths and weaknesses. What can we conclude from this analysis? Which technology emerges as the clear winner?
It's not really about declaring a single winner, is it? The choice really depends on a multitude of factors, including the specific use case performance requirements and the desired level of security.
Precisely. If we focus solely on performance, especially for tasks that can leverage specific hardware optimizations, Linux containers currently hold the advantage. However, WebAssembly is a relatively young technology with immense potential. It's already demonstrating impressive performance in certain scenarios, especially with pre-compilation and optimization techniques.
And we can't overlook the security benefits that WebAssembly brings to the table. Its sandboxed environment and capability-based security model offer a robust foundation for protecting against attacks. This, combined with its portability, makes WebAssembly a compelling choice for developers looking to build secure and portable cloud applications.
Absolutely. WebAssembly's ability to run on diverse platforms without modifications simplifies development and deployment across heterogeneous environments, a significant advantage in today's complex cloud landscape.
So it's not a clear-cut victory for either side. The best choice depends on the specific context and the priorities of the project. The research we've discussed today focuses on a specific WebAssembly implementation within Kubernetes. This raises an important question: how might these findings change with different runtimes or even outside the Kubernetes ecosystem?
That's a crucial point. We're looking at a snapshot of a rapidly evolving technological landscape. WebAssembly is gaining momentum, new runtimes are emerging, and WI is continuously being developed and expanded. The findings from this thesis provide valuable insights, but further research and experimentation are needed to fully understand WebAssembly's potential across diverse environments.
For our listeners who are actively involved in cloud development and deployment, what are some key takeaways from this deep dive? What should they be considering as they navigate this evolving landscape?
First and foremost, it's essential to recognize that WebAssembly is not just a browser technology. Its potential on the server side, especially in cloud environments, is becoming increasingly evident. Developers should explore WebAssembly's capabilities and consider its suitability for their projects, especially when portability and security are paramount.
And it's equally important to avoid assuming that Linux containers are the only viable solution for cloud deployments. WebAssembly offers compelling advantages that might be a perfect fit for specific use cases.
Absolutely. Security, regardless of the chosen technology, should always be a top priority. The thesis highlights the effectiveness of signature-based authentication for container images. Developers should adopt this practice and explore more robust tools like Cosign and Sigstore for enhanced security in production environments.
When it comes to performance, it's crucial to avoid drawing conclusions based on a single benchmark or a limited set of tests. The research we've discussed demonstrates that the performance differences between WebAssembly and Linux containers can vary widely depending on the specific task, the workload, and the level of optimization applied.
Developers need to experiment, measure, and evaluate performance within the context of their specific application requirements and choose the best tool for the job. The choice between WebAssembly and Linux containers is not a binary one. It's a nuanced decision that requires careful consideration of various factors.
This brings us to a rather thought-provoking question. The thesis focused on running WebAssembly within a containerized environment, specifically using cron, a lightweight container runtime. But what if we stepped outside this paradigm? What possibilities emerge if we consider running WebAssembly directly on bare metal without the overhead of containers?
That's a fascinating proposition. Running WebAssembly directly on bare metal could potentially unlock even greater performance gains by eliminating the containerization layer entirely.
It's like transitioning WebAssembly from being a guest in the container house to potentially building its own house, a house specifically designed and optimized for its unique capabilities.
Precisely. And this architectural shift could have profound implications for the future of cloud computing. Imagine a world where lightweight, secure, and portable WebAssembly modules become the fundamental building blocks of cloud applications.
It's a compelling vision, a world where developers can truly write code once and run it anywhere efficiently and securely without the constraints of specific hardware architectures or operating systems.
It's a vision worth exploring. And as our deep dive has shown, this exploration is already underway. The research we've discussed today represents just one piece of a much larger puzzle. It's up to all of us, researchers, developers, and cloud practitioners, to keep pushing the boundaries, experimenting, and discovering the full potential of WebAssembly in the cloud.
It sounds like we're on the verge of some really big changes in cloud computing, with WebAssembly potentially leading the way. But as with any new technology, there are always challenges that need to be addressed.
That's right. One of the biggest challenges is the development of mature tooling and infrastructure to support WebAssembly in these cloud environments. While progress is being made, we still need more robust development frameworks, debugging tools, and monitoring systems that are specifically designed for WebAssembly applications.
Yeah, it makes sense that the tools would need to catch up to the technology. And what about integration with existing cloud ecosystems? How well can WebAssembly modules interact with the services and infrastructure that are already in place?
That's another area that needs more exploration. We need standardized interfaces and protocols that will allow WebAssembly modules to communicate seamlessly with all the different services that make up a typical cloud environment.
It seems like there's still a lot of work to be done to make WebAssembly a truly first-class citizen in the cloud.
Definitely. But the potential is there. And the research we've been discussing, which focuses on WebAssembly within a specific Kubernetes environment, is a great starting point. However, as WebAssembly becomes more widely adopted, we need more research that looks at its capabilities and behavior in different settings.
So what are some of the key areas where more research is needed?
Well, we need to investigate how different WebAssembly runtimes perform across various hardware architectures and cloud platforms. We also need to analyze the security implications of running WebAssembly modules in multi-tenant environments where multiple users are sharing the same infrastructure. And of course, we need to develop best practices for securing WebAssembly applications against new and emerging threats.
It sounds like there's a lot of opportunity for researchers to really dig into WebAssembly and help guide developers and practitioners as they navigate this rapidly evolving landscape.
Absolutely. And this exploration isn't just limited to researchers. Developers and cloud practitioners also have an important role to play. They can experiment with WebAssembly, share their findings, and contribute to the development of open source tools and libraries.
It seems like a collaborative effort will be crucial to really unlock the full potential of WebAssembly.
I completely agree. The future of cloud computing isn't a predetermined path. It's shaped by innovation, experimentation, and the combined efforts of a vibrant community.
Well said. So as we wrap up this deep dive, I want to thank our listeners for joining us on this exploration of WebAssembly and Linux containers. We hope you've gained some valuable insights into these two fascinating technologies.
And remember, the future of cloud computing is constantly evolving. We encourage you to explore the resources mentioned in the show notes, stay up to date on the latest developments, and maybe even contribute to this exciting field.
That's great advice.
Yeah.
So until next time, keep learning, keep questioning, and keep diving deep.